Hello, everyone. Come on in. So turn this on. Come on in, everyone. Anybody have any questions while we're waiting for everybody to come in?
Oh, good morning.
Yeah, I do. So I noticed that for the newest lab that you posted, there is no submission button. Is that normal?
No, that's not normal. That means one of the things I might hit the radio button, which turned it back off again. My computer's slow, so sometimes when I click a button, it doesn't do anything. So I think it didn't take, or maybe I missed it. So I'll go back and click it a second time. And if I'm not watching, sometimes I actually cut it back off. So I'll have to turn that off. I will put that in the right place. Is that the lab from last week? The
Yes.
stop leaking error turn in? Okay, I'll double check that. I'll check with all the classes, make sure, because I could have made a different mistake and that would have made everybody's not show up. So I'll check them all just to make sure. Someone else tried to ask a question just before you did, I think, but all I heard was a couple syllables. Anybody recall? All right. Well, I am currently looking up to try to make sure I know what our schedule is. I want to say our midterm is supposed to be October 14th. I just put up that's weird. I just put up a respondus version of the practice test, and I'm not actually sure that it's working yet. I got to test it right after class. So don't mess with it for about 30 minutes after class, but then after that, you should be able to take it. I got to make sure it's tests for chapter 21 to 30, which obviously is in our scenario. And I actually might be really far off on the date, in which case we've got another probably 2 weeks to go. But I want to say I thought it was around October 14th. But there'll be another midterm practice that doesn't have the word respondus on it, and that's the one you take repeatedly. You just need to take the respondus one really soon, like tomorrow or today even. Just to make sure you can download everything you need, that it works with your browser and all that good stuff. So that's something I need everyone to do. Like I said, immediately. Give me about 2 hours after this class so I can verify that it's working properly. I forgot to have a class right after this, so I got to finish with them first, and then I'll check this respondus practice test. And then, like I said, don't take that respondus one more than once, because that'll waste a lot of your time, but it'll teach you what you can expect to see on the respondus portion of the midterm. And then I'll have another one up there that just says midterm practice test. So right now it shows chapters 21 to 30. So I'm thinking maybe I did set the date a little later, because for some reason I was thinking it would be up through 27 or 28 instead of 30. So we'll find out that. Does anybody have their syllabus right in front of them so they could tell us?
I think it is the 25th or 24th, if
Okay,
I recall right.
Yeah, if that's right, then yeah, that makes me feel a lot better. So yeah, that might be the case. I will double check on all that, but I'll tell you what, I'll send you an email whenever I do put up their midterm respondus. I don't know. Sometimes it's easier to do through Canvas, but it's almost always easier to not do through Canvas. So just expect it through your regular email, not through Canvas.
Quick question about that midterm practice test. Is that going to be ran through Respondus? Like, I know you said the first one is just to make sure Respondus is working. Is the second one going to be like the rest of the practice tests, or is it going to be a Respondus as well?
No, the other one's going to be just like the regular test, except it covers obviously more material, because it's going to cover up through.
No, I know that. I don't mean the material. I mean the way the test is taken, the practice midterm.
Yeah, it's going to be just like the normal ones, the normal practice.
Okay. And that's like a good sampling of what we can expect on the midterm.
Yeah, I used to say 90%, but now I've switched back to 80% of all the points you can expect to come from questions that you have access to through those practice tests. So the more times you take those practice tests, the more likely you are, if you were perfect at memorizing the right answers, to get an 80.
Okay, thank you.
No problem. Anybody else have any questions? Nada. Okay. Well, we're doing chapter 27 today, and that's usually a chapter I can finish off in a day. It might take one class period and a little bit more, I'm not sure. But either way, it's pretty straightforward. We start off with the idea of magnetism, which was something that was discovered, as your author tells us, thousands of years ago in a place in Asia Minor, which is sort of like modern day Turkey, I guess. Yeah, I think it's modern day Turkey. The place was called Magnesia, and stones from that area were found to be what we call magnets. In other words, they attracted other stones like it and stuff like that. So that's where we got the word magnet from, magnetism and all that good stuff. Over time, people realized that those magnets, if you suspended them from a string, say, or some other way where they're free to rotate, then they would actually align themselves such that what was called the north end of their magnetic pole would point towards the geographic north of the Earth. And it's not really perfect that way, because we know, for instance, the magnetic North Pole is actually in Canada, in the Arctic area of Canada, and it moves several kilometers per year. And in fact, it's reversed probably about once every million years. The poles have reversed from North Pole to South Pole, North Pole, like that. So it's not that awesomely reliable until you map it all out, which is what basically the militaries, governments, navies, and stuff like that have been doing since the 1800s. Is they've been trying to map out the magnetic field lines for the Earth as a function of location. So some places in the United States, for instance, can be off by 20 degrees, which direction is north. And if that was your only mechanism for navigation, then you want to know precisely what it is. So that's what a lot of that work has been done. We also found that there's certain metals that really get strongly magnetic, and they're called ferromagnetic, for ferrum, which is a Latin word for iron, basically. And it's cobalt, nickel, gadolinium, I think, and a couple other, the oxides of those are really the only ones we know of to be ferromagnetic. And they align themselves with basically whatever the magnetic field is. When they're in their molten form, they'll actually form magnetism parallel to that. However, the other one is something called diamagnetic, does the same thing, only it's way, way weaker, and you only can't even detect it by hand. So some diamagnetic materials, you can put two of them next to each other and not even realize they're attracting or repelling one another. And then there's another material called paramagnetic. Excuse me, that was paramagnetic I was just telling you about, sorry about that. And then diamagnetic actually orients itself opposite to the ferromagnetic, but again, is very weak, just like the paramagnetic. So para and ferra both align themselves parallel, and that should make it a little easier to remember. I don't know why I said it backwards. And then dia is like diametrically opposed, and that actually spreads itself or forms its magnetic fields anti-parallel to the existing magnetic field lines whenever it's molten. So those are sort of the materials. Your book covers more of that in detail, and that's a very interesting topic in and of itself. But this course is more about your ability to apply the laws of electricity and magnetism to real physical systems. So we don't worry too terribly much about those particular aspects in this course, but I do highly recommend you to read it to understand the concepts. So I'm actually doing some reading myself. I bought a sort of like an annotated version of Maxwell's writings, and it's basically this engineer slash physicist going through giving you an introduction to the history of each of Maxwell's papers, and then helping you understand the non-modern language. So that's kind of neat. I'll just tell you that, you know, I've been studying since I've been studying electricity and magnetism since probably 1991. And I'm still learning new stuff all the time because it's just that big of a field and that interesting. So you might try this later on, especially if you become a double E, you'll probably profit a great deal from that. So now that I got those ideas out of the way, I want to tell you that just like we did with the electric field, people imagine there existing a magnetic field. Again, basically ability to map in space, every point in space, you give it a magnetic vector, so a magnetic field vector, and that vector points in the direction of what we call the magnetic field. And it has a magnitude and direction because it is a vector, and you assign it to each X, Y, Z in space. And that's how we explain the, again, action at a distance sort of scenario. We get rid of it because we imagine the space itself carries some aspect of magnetism with it. So the space itself is actually touching the object. So it's no longer action at a distance. And we didn't really have that until really Faraday was leaning that way up until his death. And then Maxwell puts it all together and gets us more or less very conclusive proof of the existence of electric fields and magnetic fields, and giving us equations that relate all that stuff. So we have a few equations in this chapter, and they're basically, how do things behave in the presence of magnets? So the fundamental rules are: one, magnets are sort of like charges. There's a big difference, and I'm going to tell you that, but they act sort of like charges in that north poles repel each other, south poles repel each other. So like charges repel, so do like poles repel. And then unlike charges attract, so do unlike poles attract. So a north pole will attract a south pole, or a south pole will attract a north pole, but a north pole and a north pole repel, and a south pole repel. The difference is that if you take a bar magnet and you cut it in half, you don't get a north pole and a south pole. You actually get two new magnets, a north pole, south pole in this one, and a north pole, south pole in this one. And we've never been able to find anything to contradict that. So there, as best we can tell, there does not exist a magnetic monopole, which would be a single north or south pole. Sorry, my allergies jacked up. Which would be a single north or south pole all by itself. We've never been able to find that. Because of that, if you remember when we did field lines and field mapping for electric fields, we pictured the electric field lines beginning on a positive charge and then going and ending on a negative charge. So you had straight line segments as opposed to complete loops. Well, in the case of magnetism, since we never have a single charge by itself, they're always going to leave the north pole, loop back around and enter the south pole, and then go all the way through the magnet. So they're always closed loops. So that's one of the things we notice as physicists, is if we ever see anything acting in a loop-like fashion, one of the things we think of is magnetism. So if you ever look at any of these cool photographs of the surface of the sun and you see these big loopy things, us physicists look at that and we're like, yeah, that's clearly magnetism. And sure enough, it is. The sun has a seriously awesome magnetic field. So let's get started with some actual findings. Well, actually, before I do that, I'm going to go ahead and talk something else. So the big thing was, there was an idea that maybe electricity and magnetism were related. And that wasn't really nailed down until the 19th century, which is the 1800s. And more or less the first person to do that was a guy by the name of Orsted. Hans Christian Orsted, just like Hans Christian Andersen, except Orsted, O-E-R-S-T-E-D. And he basically found that when he had a wire and he had a compass near the wire, if he completed the circuit that the wire was part of by connecting it to a battery, as soon as it came connected, the magnet near the wire would actually deflect and stick in some rigid direction. And ultimately what he discovered was, if this were a wire, say, and let's say the current is going up, then if you grab it with your right hand, it's got to be your right hand now. If you grab the current with your right hand, the current carrying wire, where your thumb's pointing in the direction of the current up, and then grab it with your right hand, you then look like that. And the direction my fingers are wrapping around is the direction of the magnetic field. So you can see the magnetic field is going like this, and it's actually perpendicular to the wire. So there's a magnetic field line on this side that would be going straight out away from me or towards you. Here it would be going that way, and then here it would be going back towards me, and then back here it would be going this way. So it makes an actual smooth circle around there. That's a line of constant magnetic field. And he was also able to show that the magnetic field strength decreased as far as you got farther and farther away. It turns out it does not shrink as 1 over r squared. It actually shrinks as 1 over r, which is also consistent with what we learned for instance, infinite line of charges. They had an electric field that went like 1 over r. Well, an infinite line of current has a magnetic field that goes like 1 over r. So that was one of the things we discovered. So in that case, we actually had electric current, which we understand is pretending positive charges are running upwards. Okay, that those charges, which normally would create electric fields or would be moved by electric fields, evidently when those charges are in motion, then they can create a magnetic field. And that was a big tie-in between electricity and magnetism. And it would continue on until basically Maxwell sort of put it all together. He found some missing parts. He was able to take, even though there's a lot of papers written, he was pretty much able to just follow Faraday's writings that had no equations in it and just write out equations to make it mathematically precise what Faraday had found. And he had to add some stuff to it because he also was a very good experimentalist himself. He was able to find some things, and he was a good theoretician and a brilliant mathematician. In fact, at the time when Maxwell went to Cambridge, Cambridge was known, or Trinity College part, was known as a mecca for mathematics. That was their big deal. They were expected to be educated in the classics of literature and languages, Greek and Latin. But their final test was something called the Tripos, TRIPOS. I don't know how it's pronounced, but it was this big test. And basically, you were ranked publicly when you finished that test at the end of your years of study. Everybody took the test over, I think, a 1 week period. Like you were every day, like 8 hours of testing and huge, massive mathematical problems. And the person that came in first was called the first wrangler. And the person that came in second was the second wrangler, and so on and so forth. And that first wrangler almost always was someone brilliant. Okay. And in this case, it was also true. The first wrangler was brilliant, but Maxwell actually came in second place in that part of the test. There was another part of the test later that he came in first in, and therefore he ranked better than that other guy. But that other guy went on to just train people to become, to pass that test. So can you imagine just having the whole college rank every student by name on what they did on one test and just put it up on the wall? We're not allowed to do that anymore, and I doubt Great Britain does it anymore. I'm pretty sure Cambridge doesn't do it like that, but it's that was what it was at the time. And they would ask them really, obscure, bizarre mathematical questions that they do a great deal of work on. So when these people came out of Cambridge, they knew their math, and that was definitely the case with Maxwell. So now that we have that, and I've given you sort of the basics of finding the relationship between electricity and magnetism, I got to give you some another point, and I mentioned it already, but I didn't stress it, so I need to tell you. Whenever you see a magnet, let's say this is a bar magnet, let's say this is the north end and this is the south end. Well, I use a sort of somewhat derogatory, but not necessarily meant to be, way of remembering which way the field lines go with a magnet. Basically, just like old people, magnetic field lines leave the north and come into the south. Okay, so you probably heard thousands of times about, people retiring and moving down to Florida. That's what I mean by that. So now you can remember, okay, if I ever need to figure out what direction of magnetic field line points, I just know it leaves the North Pole, meaning it points out from the north, loops back around, and then points into the south. And for instance, that a compass basically aligns itself so that its North Pole is pointing to North geographic pole, or fairly close to it, right? It's actually the North magnetic pole that it points to. But that North magnetic pole of the Earth is actually, since it points to it, must be a South Pole. So those are two facts you need to keep in mind when you're solving problems and things like that. So let me turn on my document cam and give you some of the cool mathematical aspects of it. I've already showed you one cross product, one right-hand rule, and that was, remember that when you have a wire with a current going one direction, you put your thumb of your right hand in the direction of that conventional current, and then you wrap your fingers around it of your right hand, and that tells you the direction the magnetic field actually points. So it goes around this way. Okay, which again, you can see this way. Okay, so that's the way magnetic field lines point. If we're drawing them on a piece of paper or something like that, if it's coming out at me, I draw a circle with a dot, like I'm looking at the front of an arrowhead. If it's going into the page, then I draw it like an X, like the little feather things on the end of the arrowhead, or on the end of the arrow. So that should help you as well. We were going to learn another right-hand rule as well, and that one you either use like this with your right hand, or you use like this and curl your fingers this way. So I'll show you that later. So here's your document cam. So I've basically given you all the ideas. What was also discovered about magnetics fields is that it turns out a current carrying wire will actually be deflected by a magnetic field. Just like a current carrying wire can create a magnetic field, a current carrying wire can be deflected by a magnetic field. So for instance, let's say we have a wire. Somebody just came in, let me click that. Let's say we have a wire coming out of the page. So this is a current carrying wire and it's coming out of the page. So the current I is coming out of the page. I've drawn it that 45-degree angle, just like I do with the Z axis when I make a XYZ. Okay. And I'm going to say I is going this way. And then I will say, yeah, let's say the magnetic field is on the page and pointing to the right. So this would be my magnetic field. And that's the symbol we use for the magnetic field. And the unit we use for the magnetic field here is the Tesla. Okay, or 1T. And that is named after Nikola Tesla, who was one of the founders of electricity and magnetism. He's the reason we had 60 hertz AC in America, stuff like that. A very brilliant scientist, not that formally educated in mathematics, but still a brilliant guy. So that's what we do. Another unit that we use is the Gauss. So in that case, 1 Tesla is equal to, if I remember correctly, 10 to the 4th Gauss. I'm gonna put a question mark by that because this is something I'm going out of memory. I didn't remember to look up, but I think it's like 10,000 Gauss is the strength of 1 Tesla. So y'all can look that up yourself. That's why I'll put question marks around it. But that's another unit of the magnetic field that we use. But the rule here, I'm going to go ahead and write it this way. Basically, the force, if the magnetic field is uniform, and that means B points the same and has the same strength everywhere the wire is going through, then that F is supposed to be I times L. And we're actually going to, well, I'll do it this way, I times L cross B. That's a new mathematical operation, the cross product, that I haven't given you a lot of information about yet, but it does exist. We actually, I think I did it with I think I covered it with the torque on a electric dipole. Do y'all remember that when we covered like chapter 22 or 23? So it's that cross product. And you can see that basically I cross B, which I like to write it this way, by the way, B-I-L, but for obvious reasons, my name is Billy, right? So if you write it that way, the magnitude still works as long as you remember that you got to take the component that's perpendicular to the magnetic field. That works. But I-L cross B. So what that means is if you lay this as if it's an axle along the current, and in other words, the wire is the same as this imaginary bone that points like this, then you lay your hand across it like this, which it's really difficult because I got it coming out of the board, but you can see it easier if I do it this way. Let me show you this. So remember that was coming out of the board. So now I'm going to turn on my my actual webcam. So it's coming out of the board. So that's the current going that way. And the magnetic field was pointing this way, which is this way. It's to my right on the piece of paper, in other words. So this is coming out of the page and it's coming this way. So if I take and curl my fingers the direction that they can, otherwise I could put my hand in any of these positions whatsoever, as long as this part right here was parallel to the current. All these are fair places for me to put my hand, right? But I need my fingers to be able to curl in their natural way in the direction of the magnetic field. Well, the magnetic field is pointing this way, so I can see right there is right, and then my thumb gives me the direction of the force. So that's the right hand rule for this particular problem, says the force should be upwards. So in this case, we're going to get F pointing upward. Okay. So let's actually make some sense of that. Let's say the magnetic field B vector is equal to some B constant pointing in the I hat direction. And I'm going to call this the X direction. I'm going to call this the Y direction. And this out of the page is going to be the Z direction. Okay. I'm going to say my current I, and actually let's go ahead and say this is 1.00 Tesla times I hat. In other words, not just use a symbol B. I'll go ahead and give it a numerical value. Let's say I is equal to 2.00 amps. And let's say L, the vector, is going to be equal to, let's say it is 100 meters long and it points in the Z direction. So I'm going to say 100.0 meters in the K hat direction. So the way we can do a cross product, remember I showed you a way with using matrices. There's a bunch of different ways, obviously, but I need to calculate IL cross B. And one of the ways I showed you to do that was actually take the determinant of a 3x3 matrix, the first row of which is I hat, J hat, K hat. Okay, so IL would actually equal 200, and now this is 3 sig figs, and this is only going to have this has 4 sig figs, but I'm only allowed 3, so I have to put a 0, and let's call this amp meters in the K hat direction. So that's what I times L is. So I take that first vector in the cross product and I make it the second row. So in this case, it's going to be 0, 0, 200.0 underscore. And of course, remember the units are amps times meters, which I'll just write there to the side just to remind me. And now I'm going to take B, which is just 1.00 and then 0 and then 0. And this one, of course, has the units of Tesla. So I just write that there again. So one of the ways you can do this is you got to remember that this is the 1, 1 component, and this is a row by column. So this is 1, 2, this is 1, 3, this is 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. The reason why we do that is we can expand this on minors, and basically what you do is you choose, I always choose this row, but you can in principle choose any item in it. You could go off this one or this one or this one. But when you do, you got to write -1 to the I plus j power, where this is I, this is j, this is I, this is j, this is I, this is j. And then you're going to take and cover up the remaining items in that row and that column. So if I expanded upon I, that means this row and this column I ignore, and I take the determinant of the 2x2 matrix that's left. So in this case, I'm going to choose to go about this I, and then I got to remember this sign. So this is 1 and 1. So 1 plus 1 is 2. -1 to the 2 power is just +1. So I can just take and not multiply it by anything except the I hat. So then I take the matrix sub ij and multiply that by the determinant of the 2x2. That's really the formula. And you repeat that again for another one and another one and another one. So that's sort of the fanciness to tell you exactly how to do it. But in actually doing it, I'm going to say, okay, well, this is I hat, and that's 1 plus 1. So I don't need to change the sign. Now this part and this part's all that's left. That's a 2x2 matrix, and the 2x2 matrix always has this really simple determinant. It's down and to the right minus down and to the left. So 0 times 0 minus 200.0 amp meters times 0. So I'll put a square bracket around that. So that's what happens for the first one. Now I'm going to do the second one, which is J. So in this case, I'm going to do J, and J is has ij equal to 1 and 2. So 1 plus 2 is 3. -1 to the third power is -1 times -1, which is +1, times -1 again. So that's negative. The way I correct for that is I just go ahead and write the J with no negative sign, but I take my determinant backwards. Instead of going from top left to bottom right minus top right to bottom left, I just go in the opposite order, and that fixes it. So now I've expanded upon J. And in so doing, I've eliminated this column and this row. But I need to do it negative, so I'm going to 200.0 times 100. So I'll say 200.0 amp meters times 100, or excuse me, times 1.00 Tesla. That's this times this. Now I go minus this times this. So there's my minus, and I get 0 times 0. And that's the second term. And then finally, I'm going to get the K term. In other words, I'm going to expand upon K hat. So now I'm expanding upon this. 1 plus 3 is 4. Negative 1 to the 4th power is positive 1. So I don't have to do it backwards. I'm just going to do now, since I'm doing K, I have to eliminate this column and this row. So all I have left is this minus this. Okay, so I can see that's going to be 0. That's because of this times this, minus this times this, which is 0 times 1.00 Tesla. So ultimately, you see that my answer is just going to be 200.0 Tesla amp meters in the J hat direction, which is exactly what our right-hand rule produced. Does that make sense to everyone? Now, there is other ways you can do your determinant, and if you want me to show any of those, I'll be glad to. You can also see that I've got a couple ways on my YouTube channel, so check out my YouTube channel for other ways. Okay, so that's one of them. Now, you might say, well, that's fine and dandy, but how often do you run into a long piece of wire that's really in a uniform magnetic field? Well, you usually don't, but you can approximate it for a good section of it. Say if maybe it doesn't change that much over 1 meter, maybe you can use 1 meter of the wire to calculate the force on that particular part. And then the next meter might have a magnetic field that's fairly constant for another meter, but it's different from the first one. And of course, the orientation of the wire might be different from the first one. So you do another part for that one and add them all up. Or you can break it up into infinitesimal little lengths of line. And then when you do that, I don't want to write in red for this one. Then when you do that, you can say there exists a itty bitty force, dF, equal to I times dL cross B. And then, of course, you know that F is equal to the integral of I dL cross B. So now we've even got a integral with a cross product in it. Isn't that crazy? We had one with a dot product before. Now we got one with a cross product too. So very, very normal stuff. So let me show you how to implement this. Let's imagine this was example 1, by the way. This will be example 2. Let's imagine a piece of wire where it goes up, goes in a half circle, and then comes back down. The current is I going here, and the current is I going in there. And the magnetic field is everywhere, but I'm going to say the radius of this circle right here is R. And I'm going to say that the magnetic field is going to, let's say the magnetic field, let me see. I'm going to say the magnetic field points out of the page. The way I represent that is, again, as if we're looking at the front of an arrow. And by putting these equally spaced, I'm saying this is a uniform magnetic field over the whole separation, the whole part of the wire that we're dealing with. Okay. So we could actually create an XY coordinate system on this, and I'll do so like this. I'm going to say this is my x-axis. This is my y-axis. Notice its origin's right at the center of the circle. And of course, Z would come out of the page. So in some sense, we can say B is going to equal the magnitude of B. Let's call it B0 just to keep from being using the same symbol as the name of it. So B0 K hat. Okay. Now for this part, it's pretty easy because this part is just a straight line. And you'd say, okay, IDL is this way. And then I got to turn my right hand any way I want to until I can curl my fingers in the direction of the magnetic field, which is up. So I have to turn my hand like this. And I see that I can curl my fingers towards B this way, and my thumb points to the right. So the force here, this is the force on the right, is actually in the F direction, or is in the right direction. Similarly, when you do your hand like this, you can see that this force on the left is FL. Okay, and we could actually work that out if we wanted, but the main thing is, since the length, which I'll say this is, let's say this is y equals -2 meters, and this is also y equals -2 meters. So you see this length right here is actually 2 meters. So it's just let's actually call that L. Okay, so I times B0 times L, and it points to the right, so it's going to be positive I hat. This one, on the other hand, is going to be negative I times B0 times L. You can see those two automatically cancel each other out for this straight part of the wire and that straight part of the wire. Does everybody understand that? So remember, what I'm trying to calculate is what is the net force. On the wire. Okay, so that's what we're trying to calculate. And we're going to use our great little formula that says integral of df is equal to f, which equals the integral of I dl crossed with b. Okay, now just because this b comes after the dl, that does not mean b is not being integrated. It is being integrated. Okay, so let's keep that in mind. What I'm going to do now is try imagining dividing this little piece of wire up into little segments. Let's say this will be the angle theta, and that matches the angle theta from cylindrical or polar coordinates. And then we're going to allow it to vary a little bit by an amount d theta. Okay. And then this length right here is dl. And we can actually assign it a vector like that. We'll say dl actually has a length given by r times d theta. But in fact, it points in the theta hat direction. Okay, theta hat direction is basically, if you draw a radial line from the origin to wherever you're at, you take a line perpendicular to that and point it in the direction that theta points, or excuse me, that theta increases, then you get the theta hat vector, and it's supposed to be 1 unit long. So that's what our DL is. Okay, notice this just comes from the famous formula you know from trigonometry, which is S is equal to R times theta. So DS is equal to R times D theta. So that's where I got that idea. Does that make sense? Now, you can't just randomly use d theta when you're doing integrals, or theta hats when you're doing integrals, because theta hats are actually functions of theta and r and all sorts of good stuff. Same thing with the r hat, and same thing with the phi hat if you're doing spherical coordinates. So whenever you go to integrate something, it really is best to try to work out the details in terms of x and y, because x and y, if you use a I hat, j hat, or k hat, they're truly constant vectors, and you can just pull them out in front. So let's go working this out. What we'll see if I zoom in on that is that this is the angle theta. I think I just had somebody else come in. Yes, this is the angle theta. And in fact, if I went straight forward, this would be the angle theta as well. And then perpendicular to that is the theta hat vector. Okay, so you can see if this is horizontal, then this is 90 degrees from it, and this is theta, so this too must be theta. And you can see that this is the x component of theta hat, and this is the y component of theta hat. So this part you can see is going to be equal to, notice I need sine theta, and sine theta would be equal to opposite over hypotenuse. So if I wanted the opposite, I'd multiply it by the hypotenuse, and the opposite is the x component. And notice it points in the negative direction. So I'll say theta hat sub x is negative. The magnitude of this, which is just 1 unit, that's why it's a hat, times the sine theta, right? And then this one right here is theta hat sub y. And notice that points in the positive direction and it's touching the theta. So I'm just going to say positive cosine theta. So we can actually reinterpret the theta hat as being equal to negative sine theta I hat plus cosine theta j hat. I'm just showing you the details of what's going on at the higher level of thought here. You will see that all this is actually irrelevant, but I wanted to, I mean, somewhat irrelevant if you're wise enough to see how to use it. Okay. But that's a physical intuition that you'd have to have, which I'd argue most people don't have in their first physics course or even in their second physics course. So I'm showing you with the true mathematics of what's going on in the most direct, even though it's a area of mathematics you might not be that familiar with, you know, polar coordinates or cylindrical coordinates, that sort of thing. I'm trying to show you what all this mechanism becomes. So now I can say f is equal to the integral of, now we already said I was supposed to be just I. And I don't know why I didn't put a top on that I over here. Okay. And then DL we said was R d theta times theta hat. So I'm going to write in a negative sine theta I hat plus cosine theta j hat. And then that's got to be cross producted with the B. And we said the B0 is just, or excuse me, the B is just B0 in the K hat direction. So I'll do that. So the cross product, just like the dot product, is also a linear operator. So we can do a lot of stuff with this. I'm going to pull this negative out in front and say negative I, which is a constant, and R, which is a constant. And I might even have some more. So I'll put the integral there. And then I'll have sine theta d theta. I'll have the B0 as well. Sine theta I got right the B there. B there, sine theta, the negative's already taken care of. I got the B0 now, and then it'll be d theta times I hat cross K hat. That's one of my integrals. The other integral, notice I broke down this first term as one of the integrals. Now the second cosine cross with a K hat is going to be the other one, and that's positive. So I'll say positive. I'm also going to pull out the I, the R, and the B0. I, R, B0. And now in this case, I'm going to have the integral of positive cosine theta, d theta, and that's going to be j hat cross K hat. In parentheses. So again, this is showing you a lot of the math that you wouldn't necessarily have to figure out, because the symmetry of this, which I'll explain in a second, is going to make this a lot simpler. Okay. Now, I hat cross K hat is really wonderful because you don't have to really do any of the, matrix stuff or anything like that. All you have to do is think, what if I'll lay my fingers along I hat? Remember, that's the x-axis pointing to the right. And then I curl it towards K hat because I wanted to do I hat cross K hat. K hat's coming out of the page. So I do like this, and I see that points in the negative J hat direction. So all I got to do is say, oh, well, this is just negative J hat. Okay. Similarly, when I do J hat cross K hat, the J hat is just pointing up, and then the K hat is pointing out of the page. So I do that. That one's just going to point to the right, which is the positive I hat direction. because their magnitudes are 1, you know the magnitude's still got to be 1. So this one's going to be positive I hat. Let me make sure I did this right. So this one's I hat cross K hat. Yeah, that gives me this negative J hat. And this one's J hat cross K hat. So that gives me to the positive, right? Okay, so that's it. Now, that's really not a hard integral. The integral of sine theta d theta, we know that the derivative of cosine theta is negative sine theta. So the integral of sine theta should be negative cosine theta. And I'll get equals negative I R B0.
Oh, we can't see.
Oh, sorry. Thank you. I'm copying this down, negative I R B0. The integral of sine theta is going to be negative cosine theta. So I'll make this a positive and say cosine theta. And remember, I'm integrating from here to here. That's theta equals 0 to, that's just pi. And then that's all going to be up another negative. So now it's back to negative again times negative j hat. That's the first term. The second term is the integral of cosine. We know that the derivative of sine is cosine. So the integral of cosine should just be sine. So I'm going to say plus IRB0 times the sine of theta, again from 0 to pi. And that's going to point in the I hat direction. Now from symmetry, you should see that if you take this guy right here, this little vector right here, and that's IDL is like that, and you cross it with B, you see that that's going to point outward. So along this side, it's going to point outward, 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 boom, like that, and then outward, outward, outward. So you have just as much pointing to the right as pointing to the left. So you actually expect there to be no ultimate X component. It should be all a Y component, just from the symmetry of it. So that's the symmetry that I was telling you about, that you might be able to see a priori and throw one of these things away. I'm working it out, and we're going to try to see if we reach the same conclusion, because if we didn't, we know we made some kind of mistake, or our understanding of physics isn't right. So when I take cosine of pi, remember cosine looks like this, where this is 2 pi and this is pi. So the cosine of pi is actually -1. So I'm going to say negative IRB0 j hat. That I came from, or that negative came from this j right here, times cosine of pi is equal to -1 minus cosine of 0, which is +1, so it's -1. So we're ultimately going to get -1 minus 1, which would be -2 times this, which would be positive. The other one's going to be, remember, sine looks like this. Okay, so where that's the 2 pi, that's the pi over 2, so on and so forth. So in this case, we're going to get IRB0, and this is the one we expect to come out to be 0. But sine of pi, of course, is 0, and then sine of 0 is of course 0, so that's 0 minus 0. So it did come out to give you 0, and instead what we got is negative times a -2 gives me positive 2IRB0 j hat. That's it. That's the force. And as expected, the y components, which cancel out by symmetry, or excuse me, the X components, which cancel out by symmetry, did in fact cancel out. Any questions on that? So that is sort of all the gory details of this type of calculation. I would highly recommend you look at, this is very much like, even though I think I did the currents, I think I did the magnetic field and currents in different directions, but this is very much like the problem, example 27-3. It looks like, let me see. He did the currents the same way I did, but he did the magnetic field the opposite way that I did. So I would say, look at the simple version that the book did. That's example 27-3. So look at that one, and that's sort of using your physical intuition to avoid all this mathematics. I usually jump for the mathematics because I know I can do my mathematics correctly. And of course, I know the physics aspects of it as well, but I really, like the math part. So I tend to do the math. And not only that, I want any student that maybe doesn't feel intuitively inclined to make the smart moves that your author did in this example. I want any student to be able to fall back on just the basics of the formula and be able to crunch it out. And by me showing you this, I think I give you the details. Now you can verify this, the fact that I cross K is equal to J just by doing the determinant of the matrix. And it's a really simple one because I cross K, the first row would be I hat, J hat, K hat. The second row would be just 1, 0, 0. And the third row would be 0, 0, 1. So it's like the easiest cross product you'd ever get, but sure enough, you should get negative J hat. And the J hat cross K hat, that first row would be IJK. The second row would just be 0, 1, 0, and the third row would be 0, 0, 1. So you can verify that yourself as well. This is the actual right formula for theta hat. And in fact, if you ever wanted to do R hat, which is another helpful vector, you would see R hat really is supposed to be cosine theta I hat plus sine theta J hat. And if you take dr hat d theta, you actually get theta hat. That's the derivative of cosine is negative sine, boom. Derivative of sine is cosine, boom. So these are formulas you're perfectly welcome to use. You can put them on your equation sheets if you want. You will see them a lot, maybe in statics, but definitely in dynamics. And a lot of the stuff that you get, some of the formulas that look really obscure in dynamics, is strictly because they're taking the time to write this R in polar coordinates or in cylindrical coordinates like this. And you can do the same thing in spherical coordinates. And that's a wonderful exercise to do. But stuff like the Coriolis force that you might run into and things like that all can come from this. And you can get, for instance, a realization that the Coriolis quote unquote force, which isn't a force at all, is actually part of the acceleration in F equals ma, because you're taking a rotating coordinate system, if you will, and you're calculating the acceleration using, say, cylindrical coordinates. And part of that d2x over dt squared, which is a, comes out to be basically the Coriolis acceleration by the fact that the r hat and theta hat are actually functions of theta. So I know that's a lot of words. It's probably not making much sense to you, but it might make sense once you see it, or if you've already seen it, you probably have a little feeling for it. So any questions on that example? Let me go back from the beginning and just rehash exactly what I did. My formula for force is the integral of I dl cross B. So all I had to do is break up the line segments. In this case, the magnetic field and the orientation of the current carrying wire didn't change at all along this. So I could just use the regular I L cross B. And I'd say, okay, well, I is this way, so DL is also this way. And then of course, B points up. So I've got to adjust my hand so that I can curl my fingers in the upward direction. That means right here. So that tells me that the force is going to be to the right. And then the magnitude, of course, would just be I times L times B, which is what that is. Similarly, over here, the current's going downward. So I have to orient my hand like that. And you see the force is pointing this way. Okay. So that's that part. Now, the next part was we need to do the force for this curving part, not because the magnetic field was changing, but because the orientation of the wire was changing. The relative directions of DL and B were changing as a function of theta. So I decided to use the angle theta as one of my coordinates. And I said, okay, well, let's imagine an arbitrary point on the wire, say right here, and divide it up into a little differential segment whose length is r d theta. And that's just from the formula S equals R times theta. It says ds is equal to R d theta because it's a constant radius. So that's where the R d theta came from. And I chose it to point in a direction perpendicular to radial. The radial direction is in fact the R hat vector, cosine theta I hat plus sine theta J hat. but we didn't even need that. I just needed to realize that if this is radial, then 90 degrees in front of it gave me this angle theta being right here. So I could immediately say the x component would be negative sine theta and the y component would be positive cosine theta. So that would allow me for a brief second to use theta hat, or I could just skip that completely and just go straight to realizing the x component of this is negative sine theta and the y component of this is positive cosine theta. So I didn't have to use any of those coordinates at all. Now all I have to do is, since I have b is equal to b0k, and I know I has a magnitude I, and I know dr has a magnitude rd theta, I can just put that in there and cross it with b. At this point, I realized that if the DL is pointing this way, and the current, of course, is also going that way, then I have to orient my hand some way that this right here is parallel to that arrow. But I got to do it so that it can curl towards B. So I have to have my palm up, and then I'll see, oh, it obviously points radially outward all along there. Well, I know radially outward all the way along there starts from this position and goes all the way around to this position. That's like every possible angle between 0 and 90. And then it goes from 90 to every possible angle from 90 to 180. So I can see that the x components on this side are just as plentiful as the x components on this side, but they're in opposition to one another. In other words, this one's trying to push things to the right, this half's trying to push things to the left. So I suspect from symmetry, the j component's going to just, the I component's going to just disappear. At that point, I could just take the completely ignore the x component and only calculate the y component. In other words, I could leave this part off and just do that. And I would then get 2IRB0J, just like I did. So instead, what I did was pretend like I didn't know all that stuff and just put it in what that vector represents, and then do a cross product the component way. So basically, I'm saying this, this, and this all goes out in front of the I hat cross K hat, and the B0 comes out in front too. And that's why I got negative IRB0, that because of that negative there, that I, that R, and that B0. And all I'm left inside the integral with is d theta times sine theta times I hat cross K hat. Then when I do this term, I still have an IR B0 and a d theta, but now I have a cosine theta. So IR B0 goes here, cosine theta d theta, j hat cross K hat. And then all I have to do to compute my cross product is just compute the cross product for these two unit vectors, which is like the easiest thing you can do. And that's another way you can actually compute the cross product. You don't always have to make the matrix. You can do it like I did when I taught you dot product, or when someone taught you dot product. You could say AX I hat plus AY J hat plus AZ K hat cross with BX I hat BY J hat plus BZ K hat, and just do it term by term. And each cross product term will result in a I hat cross J hat, or I hat cross I hat, or I hat cross K hat, so on and so forth. And you don't even have to do a matrix. So all of that's fair game if you want to do it. Anyways, when I did do it, I did I hat cross K hat gave me negative J hat, again from the right hand rule, and the fact that both of these are unit long. Remember the formula, the other formula for A cross B is equal to the magnitude of A times the magnitude of B times the sine of theta, whereas A dot B was, and this is just the magnitude, by the way, was just A B cosine theta. So we use dot products to pick off parallel components. We use cross products to pick off perpendicular components. But you see the only difference here is when I do I hat cross J hat, or J hat cross K hat, or any of those, this is one and this is one. So all I'm doing is the sine of the angle between them, which is of course 90, or negative, or excuse me, the angle which is 90. So it gives you either positive 1 or negative 1. All right, so doing all that, then all I had to do was integrate cosine from 0 to pi, or excuse me, integrate sine from 0 to pi, which gave me negative cosine. So I'll put the negative there. Or I can integrate, in this case, I integrate positive cosine, which gives me positive sine. But that one turned out to give me 0, like we expected from symmetry. And the other one gave me negative 2. So any questions on that? And actually, I just looked in example 723. I think they even used the same symbols. Yeah, they did. They got 2IB. Oh no, they used R0. No, they used R. So yeah, they got 2IB times R. Same thing I got, in other words. Any questions on that? Okay. So we've got about 15 minutes left. I'm going to jump into the next part, which is how does a magnetic field affect a charged particle? Because obviously it has some effect, because when these charged particles are moving one way, you get a force given by F equals the integral of I dl cross B. But how does it actually affect a single charge? Well, that's actually pretty nice and not too hard to calculate either. So let me show you how that's done. It turns out there's a Lorentz force law, the same Lorentz that gave us the transformation equations for relativity. I don't know why I wrote R there. Oh, because I said the word relativity, that's why. Lorentz, this is a Z, by the way, force law. And this takes into account not only a magnetic field, but an electric field. But I'm just going to steal the magnetic field part. The Lorentz force law says that F is equal to Q times E, Q times E plus. I'm really liking these erasable pens. Plus Q times V cross B. So this is the force due to the electric field, and this is the force due to the magnetic field. That's the one we're going to use. So F sub B is QV cross B. So for a long time, people were trying to get charges to be affected by magnetic fields, and they couldn't get any response until ultimately discovered, oh, wait a second, when the charge is moving, I definitely get a response. And you can see here, if the velocity is 0, then you're going to get Q times 0, which is a 0 vector, and 0 vector across with anything is going to give you 0. So that's why it wasn't found for a long time, because they didn't realize, oh yeah, evidently the charge has to be moving. But that is in fact the case. So let's imagine, for instance, imagine an electron. Moving to the right at V equals 3.0 times 10 to the 5th meters per second in a magnetic field I don't know why I made that into a G. That was weird. Okay, in a magnetic field that points upward and has a magnitude oh, I don't even know what happened there. Magnitude of B equals 4.00 Tesla. That's a big, strong magnetic field. Typical MRI machine might be on the order of 1 Tesla initially, but I think now they're doing as high as maybe 10 Tesla or something. So this is a pretty impressive strength. So let's draw a coordinate system and compute what is the force. Because that's what we want to know. The force on the electron. Okay, so I'm going to draw my XY coordinate system just like this. There's X, there's Y, and of course Z comes out of the page. Everybody sees that. We're going to say that the little electron is right here and its velocity is this way. Okay, and we're going to say the magnetic field points upward. So I'm going to say the magnetic field points this way. And that's going to be 4.00 Tesla in the J hat direction. And this V, in fact, is going to be 3.00 times 10 to the 5th meters per second in the I hat direction. Now Q, the charge, is equal to negative 1.602 times 10 to the negative 19th coulombs. That's something you should commit to memory, but just about every problem I've seen in the book gives it to you. But I would definitely commit that one to memory because I'm not necessarily going to supply it. So for any midterms or stuff like that, that's just something everybody should know. The proton, of course, has the same charge, except it's positive. So we're going to compute what actually QV cross B is. So F is equal to QV cross with B. Well, QV is negative 1.602 times 10 to the negative 19th coulombs times 3.00 times 10 to the 5th meters per second I hat. And then B is going to be, of course, 4.00 Tesla in the J hat direction. If I do this math, it's pretty straightforward. 3 times negative 1.602 times 10 to the negative 19th. And I get negative 48.06 times 10 to the negative 15th coulomb meters per second in the I hat direction, cross with 4.00 T J hat. Okay, so remember I told you you don't always have to use the matrix, you can actually just use components. Well, that's what I'm going to do here. The cross product is actually a linear operator, so you can take a linear combination of vectors and another linear combination of vectors and just pull all the multiplications out in front. So in this case, I'm going to get negative 48.06 times 10 to the negative 15th coulomb meters per second times 4.00 Tesla. And I need to put a dot there so we don't confuse that with centimeters, coulomb meters per second. And then I'm just going to have this times I hat cross J hat. Well, I hat cross J hat just gives me K hat because it points out of the board. So this part I already know is just K hat. And lo and behold, I get that number times 4 gives me 192. So I got negative 192.24 times 10 to the negative 15th newtons, pointing in the K hat direction. And since it's negative, that actually means the other way. So remember, a negative charge times a velocity gives you a QV that points in the direction, the opposite direction of V. So V points this way, but since it's an electron, QV points this way. And then the magnetic field, of course, points upward. So I've got to turn my hand backwards like this. In other words, my palm has to face that way. And then I curl my fingers and that forces my right thumb to point downward, which is why we got the negative right there. Now, if I followed sig fig rules, I should only have 3 sig figs because this is all multiplication. So these 2 digits are extra. Any questions on that? All right, so that's pretty straightforward. Normal calculation you should be able to do. Again, look how easy cross products are when you just reduce it to numbers times I hat cross J hat. You can pull all these numbers that are in front of the I's and J's, you can pull them out in front of each other. And then you just have to do I hat cross J hat, I hat cross I hat cross K hat, J hat cross K hat, J hat cross I hat, J hat cross J hat, all that sort of stuff. So it's all a lot easier that way, usually. Okay, but by all means, do whatever you want. Let's look at another example. So in this example, I'm going to imagine a scenario in which an electron enters a magnetic field. And the magnetic field is going to be pointing into the page. Okay. So we see an electron, and in actuality, it could be moving a little bit out of the page, like this direction, instead of just parallel to the page. Or it could be moving a little bit this way, or it could be moving into the page, all sorts of neat stuff. But I'm just going to treat it like it's moving in the X direction. So let's say a little negative charge. That's an E minus. That means it's an electron moving that way with a velocity V. Okay. And the magnetic field has a magnitude V, 0. And of course, if I make my coordinate system X, Y, Z pointing out, then clearly this is in the K hat direction. And clearly this is, I'll call V0 as well. That's in the I hat direction. Okay. So we might want to say, well, what's going to happen with this electron? Well, as soon as it gets right here, it has a QV that points this way. So right here at this spot, say QV points this way. Well, in this case, it'd be negative EV. Okay, points that way. So maybe I'd be better to write that instead of QV. Okay. So QV points this way. B is into the page. So I can curl my fingers this way. I see immediately the magnetic field is going to cause a force pointing downward. And of course, I'm assuming that this uniform magnetic field can go on for some distance down here as well. But it's just isolated, say, at this edge. And I'm also going to assume that it's strong enough that it's going to keep it inside this area. In other words, if it's not strong enough, it's going to make it curve, but it's going to make it curve maybe in too slow of an arc. So just come out deflected out here. But I want it to actually spin completely around. So that's what I'm shooting for. So when I do that, I can see immediately that the force vector is actually going to be this way. Okay. So clearly the electron would move, say, like this position. Now the velocity is, say, this direction. The QV, that is, so negative EV is now this direction. And of course, the magnetic field still points down. So you see the force is back in this direction. And in fact, when it gets over to here, the QV, which is negative EV, is pointing that way. And now we get the F is pointing this direction. So ultimately what you see is going to happen is the electron is going to come in here and make a complete circle of radius R. Okay, again, assuming the magnetic field is strong enough to make the acceleration right. So if we take that as our what we understand is going to happen, then we can say, okay, well, QV and B are all perpendicular to each other. So QV cross B magnitude is just going to be E times V times B, which I call B0 and V0. Does that make sense? And that's the only force really acting on it, because gravity is so much weaker than the electric force. We don't have to even think about that. So I'll say the summation of forces in the, let's say the summation of the forces in the radial direction is equal to, notice it's pulling it inward, it's equal to the mass of the electron times V0 squared over that radius. because it's got to go in a circle. So the acceleration has to be the centripetal acceleration that we learned last semester. So I can say E times V0 times B0 is equal to M sub E times V0 squared over R. And that gives me that R, of course, once we make some cancellations like this V0 canceling out with one of those V0s, I can say R is going to be M sub E V0 over E B0. So that's the radius of the curve it's going to follow. I could also calculate, for instance, the period. T would equal 2 pi R over V0, right? Well, 2 pi over V0 is that. R is M sub E V0 over EB. So I now have a cyclotron frequency given by our period, given by 2 pi M sub E. Notice the V0s cancel out over E times B. And of course, the frequency, which is 1 over the period, would be E sub B over 2 pi M sub E. So that's what would happen if a charged particle goes into a magnetic field area. If that magnetic field area just starts here but goes on forever, then it doesn't matter what the strength is. It's ultimately going to form it into a circle. And in fact, if the velocity had a component this way, so we're treating the component that's in the page, but if it had this component too, it would actually go in a circle and spiral out like this, because the velocity component this direction, which is actually parallel to B, is not going to be affected by QV cross B at all. So that velocity will continue going this way. So it would come up, circle around like this, and come closer and closer to us, and in fact would make like a spring, the shape of a spring. Any questions on that? Now, of course, this is what it would happen for an electron or a proton, because they have that charge E. But in the course of the electron case, it went on a downward circle. In a proton case, it would do an upward circle like this. But if it was any other particle, you just change that with Q instead of E. And you change that mass with its mass instead of mass of the electron. You change it to the mass of the proton, for instance, if it's proton or whatever mass it is. So that's it. That's the last example that we're going to do for today. You guys are free to go. I'm going to check on your date for your midterm, and I'm going to check whether that midterm that I posted is actually working. And I'll try to send everybody an email when I know what's up with it. Everybody's free to go. I'll stick around in case anybody has any questions.
When is the midterm due?
The midterm is everybody's going to do it on the same day. So whatever date, and at the same time as class meeting. So whatever date that I put in my syllabus, that's what I'm shooting for. Now I want to give everybody, basically about 2 hours on that. So ideally, if you could start, up to maybe 45 minutes early, or stay, up to an hour late or something like that, that would make it easier for you to fit the whole 2 hours in. But if any of y'all have a problem where you can't do that, I'll have to make another test, and you can take it at some other time where you can fit the whole 2 hours in. I don't think it'll take me 2 hours, but I want to give you 2 hours.
And have you decided whether we'll have to scan in our work and show it or not yet?
No, I haven't decided, and you only know when you get on the test whether I'm getting you to do that or not. So it'll say it right on the question. So be prepared, like, you're not allowed to use your phone during the thing, and if it catches you, they would mark you as cheating. So you want to have it out of arm's reach from where you're sitting, because when you use the respondus, it's going to make you video the work area. You don't want that in your scene. Okay, but as soon as you submit the test, then you can grab your phone, and if you kept it on silent, you could have left it on the whole time, and then you can take a snapshot of it and email it to me. I usually give you 15-20 minutes to get that done. Anybody else?
So I'm assuming you're just gonna open up the submission thing for a last lab in like a few days.
I'll probably do it today while I'm remembering, hopefully.
Okay,
Okay.
that's it.
All right. Thanks, Rodo. Anybody else?
Have a good one.
You too. Take care, everybody.
Have a nice one.